Okay, so it's my pleasure to introduce Bernardo Subercaseaux, who is a PhD student at Carnegie Mellon University, and he's an expert in set, and I believe interested in many other topics. So, a few intuition.
Thank you. So yeah, I'll be talking about set solvers in mathematical discovery. So similar, but also a different flavor. So I'll start by setting the scene with a quote that summarizes a bit of my point of view with respect to this by Jordan Ellenberg. So it says, what's most exciting to me is modeling new modes of human and machine collaboration. I don't look to use this as a replacement for human mathematicians, but as a force multiplier. And I'll try to show, by way of example, how set solving can be a force multiplier in mathematics. So first, I want to refer to a very nice talk by Terence Tao from 2024, where he gives a historical, broader context about the role of computation in mathematics. So starting from the abacus, going to tables that were used, for example, for the prime number theory, to now online encyclopedias or classifications of elliptic curves, for example, to computer algebra systems like Maple, Sage, Mathematica that many of you might be familiar with, to set solvers, formal theorem provers like Lean that we were discussing yesterday, and maybe, who knows, LLMs entering the picture. But in particular, today I'll be talking about something that's not the newest, but also not as old as the abacus, and yet for which I believe that there's a lot of use today. So you, I guess, definitely have already heard about set solvers in mathematics based on the previous talk. And there's several other examples of famous either theorems or counterexamples that have been found through set solving in a variety of domains, often related to discrete mathematics, but not necessarily insofar sometimes there's problems in other areas of math that can be discretized and then are subject to being treated by a computer. I won't actually be talking about any of this today, though. These all follow kind of a common pattern where you use set solvers to tackle a combinatorial problem where in principle you could have used brute force and that would just have been extremely inefficient. So there's like some sort of efficiency constraint in place. I'll be talking about how some solvers can be also used at different stages of mathematical research, maybe more at the beginning rather than finishing a theorem, how you can use them to build examples, counterexamples to your own ideas, and how they can elicit conjectures that you might try to prove or disprove later. So my vision as a kind of silly syllogism is that first, counterexamples or examples help drive mathematical progress. My second premise is that finding such examples or counterexamples can be NP-hard, and sometimes provably so. And the third premise is that set solvers solve instances of these NP-hard problems efficiently in practice, so in a way that can be incorporated into the mathematical practice. My conclusion with some leaps in between that I'll try to iron during the talk is that if you mix these three premises, it feels like set solvers can help drive mathematical progress. And I'll try to give the appropriate caveats throughout my talk. So first, to talk a bit about this role of examples and counterexamples in mathematics, I wanted to do something that people usually advise against in talks, which is to read a long quote by somebody. But I think in this particular case is really warranted. And this is in a particular piece of Euler that in English would be titled Example of the Use of Observation in Pure Mathematics. So it's really about what that role can be. So it says, it will seem not a little paradoxical to ascribe a great importance to observations, even in the part of mathematical sciences which is usually called pure mathematics. Since the current opinion is that observations are restricted to physical objects that make impressions on the senses, as we must refer the numbers to the pure intellect alone, we can hardly understand how observations and quasi-experiments can be of use in investigating the nature of numbers. Yet, in fact, as I shall show here with very good reasons, the properties of the numbers known today have been mostly discovered by observation and discovered long before their truth has been confirmed by rigid demonstrations. The second part is that there are even many properties of the numbers with which we're well acquainted, but which we are not yet able to prove. Only observations have led us to their knowledge. Hence, we see that in the theory of numbers, which is still very imperfect, we can place our highest hopes in observations. They will lead us continually to new properties, which we shall endeavor to prove afterwards. The kind of knowledge which is supported only by observations and is not yet proved must be carefully distinguished from the truth. It is gained by induction, as we usually say. Yet we have seen cases in which mere induction led to error. Therefore, we should take great care not to accept as true such properties of the numbers which we have discovered by observation and which are supported by induction alone. Indeed, we should use such a discovery as an opportunity to investigate more exactly the properties discovered and to prove or disprove them. In both cases, we may learn something useful. And thanks to Jeremy that gave me the reference where I found this quote. It's in a very nice book by George Polya. So in the next 45 minutes, my plan is to convince you that solvers are actually easy to use. There's really nothing scary about them. Hopefully, I can demystify them a bit now, and it should be fully clear by the tutorial tomorrow that you can learn how to use them very quickly. I'll try to convince you that they can be a powerful tool for assisting discrete mathematical research, and that as opposed to some newer technologies, they are free of hallucination. So first, I wanted to start with a quick Q&A about some questions I'm predicting people might have, just to set a bit of the notation and nomenclature I'll be using. So what is a SAT solver? Well, it's a highly optimized program for deciding if a Boolean formula is satisfiable. So it's programs optimized for one particular task. A Boolean formula, well, I mean something that looks like this. So it was, I think, very well explained in the previous talk. Satisfiable, I mean that there's an assignment of the variables, in this case, 0, 1, 0. So the x1 being false, x2 being true, and x3 being false. That satisfies this formula. And immediately a question is like, well, how do I write this on my computer? So the answer is there's standard formats in which you directly write your formula. So here I'm saying that it's a conjunctive normal form formula with 3 variables and 2 clauses. The first one is x1 minus x2. That's the negation. x3, 0 for termination, and so on. Now, writing your formulas this way would be, of course, unsustainable. So usually what you do is you write code in, let's say, Python, C, whatever language you prefer, that will write a file with this formula, and then you run it. Then what happens? Well, there's a couple of possible outcomes. So you might run it, and it might tell you that your formula is satisfiable, in which case you get directly an assignment of the variables that satisfies the formula. Or you might get the solver to say that this formula is unsatisfiable, in which case there's no such assignment. I'll be mentioning this at the very end, but you can also get a reproducible proof of this fact. It's not just the word unsatisfiable, and you're like, oh, OK, I guess I might have to believe that. And finally, just to present one of the possible caveats, is that even though this surely terminates in theory, in practice, the outcome might be that your problem is a bit out of reach. So a question I think it's very natural to have when people talk about SAT solvers is like, well, isn't this an NP-complete problem? Sometimes in like in certain talks, even NP-completeness is sort of seen as like where things end. It's like, oh yeah, we cannot do that. It's NP-hard. But sometimes it's also where interesting things begin. So SAT is indeed an NP-complete problem, and that's actually precisely what makes it so nice for this application, because it means that it's hard, which implies that writing your own efficient algorithm is a large engineering challenge. It's very hard to compete with, a leading solver yourself. So if you have any NP-hard problem, which is not exactly SAT, odds are that a SAT solver will be more efficient than anything you can write yourself easily. And the completeness part means that it's universal, which is to say that it can represent a lot of different math problems in a variety of different objects like graphs, matroids, groups, even geometry, as I will be talking about today. So let me start with a toy example, just to start nice and easy. So a problem that's actually NP-hard when it's like n by n as opposed to 9 by 9 is Sudokus. And on the right, I have the sort of human constraints that define a valid solution. So each cell must contain a number from 1 through 9. Each number from 1 through 9 needs to appear exactly once per row, column, and these 3 by 3 major subgrids. So the first thing to think when you're encoding a problem into set is what your variables should be. And here, a very reasonable answer is to have variables indexed by ijn, saying that cell ij gets number n. So when we put this into code, and I don't want to put that much attention into code, but I do want to show that the code is not complicated. It's very direct to how you write the constraints in a whiteboard. So here I'm creating these variables xijn. The constraint that each cell must contain a number from 1 through 9 in sort of whiteboard logical notation is just a big OR that we're doing for each tuple ij. We need to force that the clues of the puzzle are respected, right? The puzzle is given with some clues, which come down to clauses that don't have an OR inside because they have only one literal in there. So it's like you're forced to take that as true. So the code for this is, again, quite direct. The clause is just a list of the literals. And for the clues, it's just a list with a single element. Now, more interesting, how to encode that exactly one of a list of variables is true. So exactly one is a combination, of course, of two things, of saying at least one, which is trivial, is just to say one clause that says that one of those variables is true. And at most one, which in its naive form corresponds to, for every pair, saying that that pair cannot occur simultaneously. That's a way of saying that at most one thing can be true. And that, as you can see, I don't really like because it's using a quadratic number of clauses. So if all we have are these variables x1 through xn, it's actually easy to show that there's no other more efficient way than this naive form. But there's a way to do better, and it's by introducing some auxiliary variables that summarize information of the problem. So let me show you exactly how that looks like. So suppose, bear with me for a second, that we have some variable y that summarizes whether a variable in x1, x2, x3 is true. So if one variable in that set is true, then y is true. If no variables there is true, then y is false. So suppose I have this magical variable that is summarizing this information about now a group of variables. What can I do with that? Well, now I can say that at most one between y and the rest is true, because y is summarizing x1 through x3. OK. And how do I get my assumption? Well, I can get it this way. Now, if one of the x1 through x3 is true, the fact that I'm saying that at most one of this is true will imply that this is false. And because this is false, y is true. So what that means is that encoding at most one, introducing this new variable y, can be done recursively in this way. And the number of clauses now satisfies that f of n equals f of 4 plus f of n minus 2. So I'm using a constant term to chop a constant fraction of my problem, so the solution is linear. And this is just the tip of the iceberg of what nice encodings are. But the point I'm trying to make with this slide is that encoding things efficiently can be an interesting algorithmic or mathematical challenge on its own. And there's some really cool encodings out there. Now, when you write this in code in any library worth its name, usually you won't actually have to write that manually, but rather there will be high-level primitives that say like exactly one, and you give it the list of variables, and it will do this efficiently for you. And similarly, if you want to say that exactly k of your variables, or that at least k of your variables are true, all of those are usually hinted either natively by the library that's doing an encoding, as I showed, introducing new variables, or by a solver that has native support for them. So you don't have to worry about those details when you're writing an encoding. Okay, so Sudoku, an example to get started, but now let's start getting into some more mathy examples. So the main idea here is to gain insight on a mathematical problem by searching for finite objects. And then the hope is that the existence or non-existence of these finite objects will be encoded in a Boolean formula. So the formula is satisfiable if the object I'm looking for exists. And hopefully that can give us some insight. So I'll start with a couple of classic old problems whose answers are fully known and that they have decently short human proofs, but that came after Euler and are examples where you can get this kind of observation that leads you to what the right answer is. So here's a question that Mantel posed in the 18th century. What's the maximum number of edges on a triangle-free graph on n vertices? So it's like the two properties that oppose each other. So you want to have as many edges as possible, but you also want to avoid triangles in your graph. And if you think about this problem for a tiny bit, you should come up with the fact that the full bipartite graph seems like a pretty good idea here. It doesn't have triangles because it's a bipartite graph, and it seems to have a lot of edges because I literally put as many as I could with the restriction of being bipartite. Now the questions are, of course, could we have more edges than this? And also, is there an non-isomorphic construction that also achieves the same? Perhaps this is one way of doing it, but there could be others. And actually proving that manually turns out to be much harder than just proving that this is optimal. So this is actually the full encoding of Mantel's problem into set. It's this short. I'm adding variables EUV to encode whether in my graph, in the graph I'm looking for, there will be an edge between vertices U and B. Then I'm just saying that there will be no triangles, and I'm doing that with a triple for loop, where for every triple UVW, I'm saying that at least one of the edges is missing. So it's a clause that has 3 negative edge variables. At least one of the edges is missing. And finally, I just say that I have at least m edges. So this method receives the number of vertices, the number of edges, and it encodes, is there a graph with that many vertices, that many edges that has no triangles? Yes?
This example and also the Sudoku example, essentially what are you just or is the kind of procedure to say if the Sudoku puzzle is solvable, is to literally enumerate all possible digit evaluations?
Right. So no. And that's very important because there's too many of those. There's too many graphs, for example. I will not show exactly how to get that right now, but I'll show almost that. You can get Mantel's theorem automatically up to n equals 50 in the computer, for example, with that solving. And there's way too many 50 vertices graphs, right? So the solver is doing something much smarter than trying all evaluations. Now, exactly what it's doing, I will not be talking much in this talk. It's like it requires a lot, an entire, I think, in my opinion, talk on its own to actually see why there's even opportunity to do better than listing everything. But there is opportunity to do better than listing everything. So you can see up to some finite n by encoding this that there's no way of getting more edges. So of course, this is not telling you that this is true for any n. It's just telling you until whatever n you manage to solve on your computer. What about the question of a non-isomorphic solution to this? How can we tackle that with SAT? So for that, I'll talk about a bit about symmetry breaking, a very important technique to speed up SAT solving. So first, a mathematical observation. If the sum of degrees in my graph is 2m, twice the number of edges, just the handshake lemma, then some vertex has degree at least 2m over n, right? I'm like splitting things. Somebody has to be lucky and get at least the average. And without loss of generality, that's like the mathematical keyword that you map to symmetry breaking in SAT solving. That vertex is vertex 0, and it's 2m over n neighbors I decide that are just like the ones that come after in the natural ordering. So how do I encode that? Well, I just force that those edges are there. I know that I can assume that without loss of generality, so I just tell the solver to assume those edges. Now, this on its own, it's not enough to break all symmetries of the problem. The problem still has a lot of symmetries. But if we also force the edges of 0 to be sorted, meaning that 0 is connected to all vertices up to some I, which matches its degree, and then non-connected to everyone afterwards, then there's actually a unique solution, and the set solver figures that out. How do you actually figure that out with the set solver? Well, you run the formula, you get a solution, and what you do after is that you block it. You say that at least one of the variables in the solution you got must be false. So that's one extra clause. And now the set solver tries to solve the problem of your previous formula with the block solution. And now it tells you that there's no solution, which means that your previous solution was unique. And as you can see in this humble plot, the effect of symmetry breaking is allowing you to solve the problem to a further n. And this kind of picture is usually what you will see in stat solvings. You're pushing forward an exponential curve. You're not changing really its nature. One way or the other, the exponential nature of the problem will bite you, but you can try to postpone it, and sometimes that's good enough for a lot of practical applications. Now a more algebraic example. This is like the very, very, very baby version of what we were saying in the last talk. So Lagrange theorem says that for every subgroup H of a finite group G, the kernality of H divides the kernality of G. So we can encode given numbers n and k whether there exists a group of size n with a subgroup of size k. And if we encode that and run that formula, we'll get that 8.1, 8.2, 8.4, 8.8 are sat, and the other 8k cases are unsat. So you make this table up to, for example, 12 is very easy to do with sat. And you already have, if you look at that table, a pretty big hint that what's happening here is exactly the divisibility rule. Now, how do you encode that? Well, it's pretty direct from what the definitions are. So you encode a multiplication table, in this case, a variable mijk, saying that I times j equals k. Then I want to say that this is actually like a table and not some other structure. So I need to say that I times j has a unique answer. There's only one of those variables that is true. I assume without loss of generality that the neutral element is the one indexed by 0. So then I force that 0 times I is I times 0 is I as well. I need to force some concept of inversion. So I can create variables inv ij that represent that I and j are, that I is the inverse of j. Now I need to say that each element has an inverse. I'm connecting that to the multiplication table. I'm encoding associativity, which is the most annoying one to do. I'll use some indicator variables for which elements are part of the subgroup. The neutral element needs to be there. I need the subgroup to be closed under inversion. So if I is in the subgroup and its inverse is j, then j must be in the subgroup. I need this closure. And finally, the subgroup size is, again, one of these kernality constraints where I just say exactly k of these indicator variables are true. OK, that's cool. The proof of that is actually pretty simple. But a cool question you can ask is, what about the converse of this theorem? Is there a group on n elements and some divisor d of n such that j has no subgroup of size d? And this is actually true up to 11, but it fails. The converse fails at 12 because there is a group on 12 elements without subgroups of size 6. And this you can also get through SAT. It's a much longer computation, but it's definitely doable. And it has an interesting thing going on, which is that this actually is not quite an existential statement in the SAT form. I'm saying, is there a group such that for all its subsets of this size, they cannot form a subgroup? So it's like an existential for all question that's usually beyond SAT. But the trick here is something I learned from my advisor, Ryan, is that when n is small, you can just afford to unroll the exponential thing, because there's only 12 to 6, which is 900 something possibilities. So you just take all the possible 6-element subsets of 12 elements, and you say none of this is a subgroup. And that gets you, again, an existential formula. So after these examples, I want to read a quote by now Tarski that says, however, the machine would permit us to test the hypothesis for any special value of n. We could carry out such tests for a sequence of consecutive values, 2, 3, up to, say, 100. If the result of at least one test were negative, the hypothesis would prove to be false. Otherwise, our confidence in the hypothesis would increase, and we should feel encouraged to attempt establishing the hypothesis by means of a normal mathematical proof, instead of trying to construct a counterexample. So my point here is to say that SAT solvers are, in a way, an embodiment of Tarski's dream. And there's cool examples where not only you get to 100, but you get to several thousands, like in the Pythagorean triples problem that my advisor solved. So it can go even beyond, I guess, Tarski's dream in the 1950s. Now some examples from discrete geometry that I've been working in the last couple of years. So the question that sort of kick-started the whole geometrical Ramsey theory is how many points without 3 of them on a line guarantee that you have a convex quadrilateral. And the answer is just 5. This is known as the happy ending theorem proven by Esther Klein. So a neat way of proving this is by considering 3 cases, depending on how many points are on the convex hull of the 5 points that I have on the plane. So if I have 5 points in the convex hull, I just take any 4 of them, and that gives me a convex quadrilateral. That's very simple. If I have 4 points in the convex hull, I just take the convex hull. That gives me a convex quadrilateral. The last case is the only one that hints at something actually interesting, which is what happens if I have 3 points in the convex hull. And here the trick is to imagine the line that goes through the 2 points that are inside the convex hull. And now it must be the case that on one of the sides of this line, there are 2 points. So this forms a convex quadrilateral. Just as a side remark, but there's a very nice proof of this I learned recently, where you use the fact that a quadrilateral is convex if and only if its diagonals cross. And after that, this fact is equivalent to say that there's no planar drawing of the K5 graph, because the crossing of the diagonals implies the convexity of the quadrilateral. So you're forced to have diagonals cross in a planar drawing of K5. You're forced to have a convex quadrilateral. OK, so some interesting lesson of the previous proof is that we were actually making a statement about any kind of position of points on the plane on R2, but we only required a very combinatorial form of reasoning to tackle this question, just to case on where points are located with respect to each other rather than their precise locations, which don't really matter for this question. So the insight from this is that we can define variables parameterized by 3 indices, A, B, C, that represent whether A, B, C, that kind of curve, is counterclockwise or clockwise. Those are the only 2 cases, because by assumption, as I said, there's no 3 collinear points in my sets. So it's like either positive or negative. And just to be fully formal of what counterclockwise mean, I mean that this determinant is positive. So just for an immediate example of why this is useful is that a polygon is convex if and only if the turns in cyclic order are either all clockwise or all counterclockwise. So as you can see on the image on the left, all the turns are clockwise. If I'm iterating in that direction, I could also iterate in the other direction. They would be all counterclockwise. Whereas on the non-convex 5-gon on the right, I have like a change in the sense of the turns, which is exactly what happens when you sort of figure out that your polygon is non-convex. So just these variables representing the orientation of my turns are enough to characterize convexity. Now here's an interesting application on a paper we published a couple of years ago. It's a question that Erdős posed in the 1970s. Given an integer n, what is the minimum number of convex pentagons we can get by placing endpoints in the Euclidean plane without 3 of them on a common line? So if we have 4 points on the plane, what's the minimum number of convex pentagons we can get? Well, this is a trick question. The answer is, of course, 0, right? We just put them somewhere. The answer is 0 convex pentagons. What if it's 8 points? How many convex pentagons is the minimum I can get? And the answer is, again, 0. You put them that way, and there's no convex pentagon you can form with those points. Now, I don't expect you to be able to verify that mentally, but hopefully it looks believable. And if you make a table of this function, here's the first point where you're forced to have at least 1 convex pentagon. That's a generalization of the Esther-Klein proof that we saw earlier. And for 15, the answer turns out to be 77. That was not known before our work. And I'll try to show you why actually knowing these numbers is useful. And it's useful because it hints you at what the right answer is. So we ran some local search. And these are the numbers we got with the light blue highlighting to represent some numbers that were not known before. So of course, as I was saying before, at some point, the exponential ends up biting you. Now we're talking about several hours. And actually, this is the only one of these numbers that's wrong, where the local search trying to minimize this did not get to the actual optimal number, which should be actually 6,006. But already with this data, if you put this in Mathematica, there's something you can realize, which is that it really suggests that this is the formula of what's happening. And that's matching all the blue points until here. And this one is off by 1. Sorry, yes?
How do you know about the optimality?
Yeah, so you can, so verifying the optimality of, so I don't want to get too much into details. Here we're solving a maxsat problem in where we're trying to minimize the number of convex pentagons. And there is work on verification of maxsat. So you can get verified solutions here until a smaller value of n. So here, this table is not a verified table in the sense that this is local search, where we're giving the solver the problem and asking it to do the best it can do to minimize. And it will give you a number which is only an upper bound, because it's like, I found this way, and I don't know how to do better. But until here, we have fully verified the results. Now, it's interesting that you asked that, because part of the reason also where you can see these formulas is sometimes based on unverified data. Sometimes verifying is much more expensive than having a hint of what the solution is. So it's interesting that already with unverified data, you can formulate a construction. Now, when you get a solution from the solver here, it's just telling you these variables about which turns are clockwise and counterclockwise. Now, how to know what that looks like in the plane? How do I draw those points? So now my problem can be seen as the following. I need to find these real numbered variables, x, y, for each point, its coordinates on the plane, based on the fact that they all satisfy these determinant conditions that I show. And determinant conditions are, of course, a polynomial condition. So we have like these real variables and this polynomial conditions. So this turns out to be complete for the complexity class of the existential theory of the reals, which is to say it's actually harder than SAT, meaning that, or believed to be harder than SAT. So actually finding how the points look like on the plane is actually harder than finding what their assignments should be like. But I made a program that tackles this realizability problem through local search, and it turns out that it works pretty well in practice. And with that, you can see, this is for n equals 12, how basically all the solutions we found look like, either like the picture on the left or the one on the right. So basically what we did, or in particular what the mathematician on our team did, is like, well, this seems like general constructions, because not only we got that for 12, but also for further numbers, we were able to visualize how these solutions were looking like, and it felt like they were falling into these two categories of solutions. So a way of seeing, of thinking about this parabolic construction is that actually, if you draw these parabolas correctly in opposite directions, every subset of 5 points on one of the parabolas, like on the left example, will be convex. But any set that spans the two parabolas will be non-convex. And remember what the conjecture formula was. N over 2 choose 5 with the ceiling, and N over 2 choose 5 with the floor, which is exactly what happens when you have to divide N in like two parabolas. And in each of them, all the 5-point subsets are convex. So it's pretty cool. This construction gives you exactly the formula as an upper bound. And just to say something, this is not trivial insofar you need to actually be careful about the shape of the parabolas. If they are like too open, as on the picture on the left, you can get convex polygons that span the two parabolas. But if they're like close enough, they actually end up looking a bit like straight lines, but they are actually parabolas. Then you're guaranteed this property, and you can prove it from the concrete equation. Sorry, you had a question.
Yeah, what wasn't clear to me was, did you guys come up with the parabolic constructions from using the SAT solver and making graphs with the SAT solver, or did you just come up with it on your own? It's not clear.
Right.
Look at this geometrically.
Right. So there's a couple of things to say there, but so actually the way we describe it is that John Mackey, who was the person in our team that actually came up with the concrete equations, he was thinking of the parabolic construction before, but not of the other one.
Okay.
So actually he already was thinking that this was a good way of doing it without knowing how close was it to optimal or anything like that. Then, so it was, yeah, like not like full on in the order that we didn't know anything, we coded and we got the idea, but rather he had this idea first without really knowing how good it was or something. Then we got the data, so we were able to see that this was actually optimal up to some point. And we also found this one where it's actually significantly harder to see why this also gives exactly the same formula, but it does. You can analyze it, and we have it on the paper. Now, on to another problem that I'll call the distance digits problem. This is actually a sort of a serendipitous story that happened to me like 2 months ago with a question I just saw on Stack Exchange. So somebody was asking about this problem that is basically, can we have n squared many words over the alphabet 0 to n minus 1, the words having length n plus 1, and where they all have the same Hamming distance from each other. So it has some heavy coding theory kind of flavor, even though the person who asked the question says that they were starting with a problem in n-dimensional Euclidean geometry, and it came up to this combinatorial thing. And they give an example for 3, where you can see that all these words here are a distance 3 from each other. So any pair of words there is at Hamming distance 3. And I encoded this, and they said that they actually cared up to like 10. So I was like, OK, there's a chance I can just solve this with SAT. And what I did is that I encoded this to SAT. The solution for 3 is trivial to find, and I found a solution for 4 and for 5 right away, not hard at all. But I was not being able to find a solution for 6. And so I started to look a bit further into the solutions I was finding for 5, because I was trying to see if there's some symmetry breaking I can do there that then will allow me to solve 6. So that was my plan. And sometimes I show in the mental example some symmetry breaking property that you can prove. You can prove that this you can assume without loss of generality. But sometimes you can also enforce a symmetry breaking predicate that you don't actually know if it's without loss of generality. But you can put in there and see what happens. And if there is a solution, you're happy with it. So I was trying to see if I could find something like that. So a thing I started trying is like, well, can I assume for 5 that there will be a string that's 5 zeros? And I get a solution. And I was like, OK, I can assume that with loss of generality. And that's actually easy to prove that you can do in general because, yeah. And then I was trying, well, can I assume then that I have something that's also 0 and then all ones? So I started like adding constraints, seeing if at some point this became unsatisfiable. And by doing that, I found this very cool solution that looks, as you can see, pretty structured. So I'm sort of being, I'm doing a little like mental trick here where I'm like coloring and putting things into a group in a way that's maybe more suggestive that what you actually get as an output from the computer. But you can see the first group, it feels like everything is kind of aligned. The second group, where everything starts with 1, you can see that it's sort of like shifting by 1 every time. In the second group, it's shifting by 2 every time, mod 5. And similarly on the other groups. So how to define these strings? It's like, well, I'll say that S of A comma B is the string number B from block A, both indexed from 0. So basically, for example, this is block number 3. So it starts with 3. So the first digit is A. And then the digit I is A times I plus B mod 5. That's just like putting in a formula what we were saying about the shifting. Now, considering the following claim, I claim that these strings, according to this construction, have exactly one position in which they match. So if I take any 2 strings from here, there will be exactly one position where they match. And the proof is actually surprisingly simple. So there's 2 cases. If they are on the same block, then that's already one match because they match on the first digit. So then my goal is to show you that there's no other matches. And any other match, by the definition, would be that this is congruent to that modulo 5. But that is to say, because they're on the same block, this term is the same as that one. So that will be that B1 equals B2. So I'm talking about the same string. So it's not 2 different strings. The second case, where they're on different blocks, means that they obviously don't match in the first symbol. So they match somewhere else. Now I can factor this equation as follows. And this has a unique solution because now A1 minus A2 is non-zero. So it has a unique inverse since 5 is prime. So I'm actually working here in a field. And actually, what's nice about this is that by looking at this, I got that this holds for any prime. And then it's not, and then you can do this for any prime power as well. Funnily enough, then 6 is the only number below 10 for which then I don't know the answer, because 8 is 2 to the 3, 9 is 3 to the 2, 7 is prime. And I actually still don't know the answer for 6. But I do now know it for an infinite set based on a finite computation. And finally, or I guess second to last topic I wanted to show is about applications of that solving to theoretical computer science now, as opposed to, I guess, discrete mathematic research. So some kind of like combinatorial kind of game that theoretical computer science have sometimes to play is to find an NP-hardness gadget to prove that some problem is NP-hard. And these gadgets can be actually some sophisticated constructions. So here's, for example, an example of a random paper I took where they prove that some graph problem is NP-hard, and they need, in the reduction, to construct this as a subgraph. And one can often wonder, well, how did they find that? And I don't know the answer, but I'll show you the answer of how I am finding some of my gadgets these days. So here's another example from a paper on collision detection for robots, where they're like trying to show that some problem about robots that are like on some common, let's say on a common factory, are not like bumping into each other. They're like all doing the trajectories without crossing. And they reduce from SAT, from the NP complete problem of satisfiability in formulas with 3 literals per clause. So they have to construct these gadgets that represent, for example, a variable, something that's true or false, a gadget for the clauses, for connecting variables, and so on. So again, this is a combinatorial construction that who knows how they specifically came up with this. And here's one of my favorite examples of a cool gadget. This is from the proof that Super Mario Bros. Is NP-hard. And it's also a reduction from SAT. And the gadget is very cool, actually. Mario, in a variable, needs to choose if he jumps on the left side or on the right side, which represent true and false. And the clause gadgets basically are saying that in order to break this wall, that you need to keep moving, because the problem here is to decide whether Mario can do this, you need to jump on one of these 3 turtles. So at least one of these needs to be true. And these turtles come from one of the paths of different variables. So if you jump into it, so you need to have jumped that way so that you can bump into a turtle that then falls and breaks the block. So it's pretty clever, honestly. And this is actually just one in the paper. They have even more sophisticated gadgets there. So how do you find this? Well, I'll show you a couple of examples of gadgets that I've found through SAT solving. So here's a classic, very old NP-hard problem that's called feedback vertex set. And the goal here is that, or the situation here is that you get a directed graph, and the goal is to remove the minimum number of vertices so that the resulting graph has no directed cycles. So let me show you a bit with an example in this graph. Here are the directed cycles that are present in my graph. So what should I remove in order to guarantee that my graph is acyclic? I'll take the solution from the audience. Any ideas? The vertex in the top, that's exactly right, because they all have it, right? So if I get rid of that one, I'm getting rid of all the cycles. And I cannot do it with 0 because I have cycles. So that's the solution. So I remove that, and I get this as a resulting graph that has no directed cycles. OK, so that's feedback vertex set. Now, the fact that this is NP-hard, I think, was known in the late 70s already, and the reduction is actually quite simple from vertex cover. So in vertex cover, just as a reminder, you're trying to select a smallest subset of your graph. Sorry, I think, yeah, so you're trying to select a smallest subset of your graph such that all the edges are touched by that subset. So in particular, here, the pink subset is touching all of the edges. Another way of saying that is that you want a minimum number of vertices such that if you remove them, now your graph has no edges. It's independent. So actually, all you have to do to get feedback vertex set is to replace each edge by a directed cycle of size 2. And now it so happens that now to get rid of the cycles, you need to break each of these, which is the same as breaking each of the edges originally. OK, so this is a very as simple as an NP hardness proof can get. Now, what I needed to prove in a paper of mine for LPART 2024 was that feedback vertex set is also NP-hard on 3 out-regular graphs, so where each vertex has 3 outgoing neighbors, and also where you don't have C2s, so cycles of length 2, in your graph. So kind of explicitly, by the restrictions of my problem, the standard construction was banned. And just notice that the 3 out-regular thing is not that big of an obstacle because vertex cover is also NP-hard on 3 regular graphs. So that's not the biggest obstacle here. So one of the first things I thought when I faced this was like, well, I can maybe just like cheat a little bit and surpass my band by adding like one auxiliary vertex here and replacing my cycle of size 2 by a cycle of size 3. Now, part of the issue here is that I'm breaking this 3 out regularity thing because I introduced this like new vertex here that now has just 1 out neighbor. So it's like who am I going to connect it to so that I still am in control of not having cycles, introducing new directed cycles that I don't want. So the question that I was facing then is, can I attach to the green vertex a 3 out regular C2 free graph where I know, about its directed cycles. And obviously, in that graph, the green vertex should have out degree 2 instead of 3 because I'm already counting 1 here. And the answer is yes. And I just encoded that as a SAT problem, and it gave me the solution. And it's this. And this is the smallest example with the properties I desired. Now, there's something even cooler about after doing this, because after I found one solution, I was trying to see if there were other ones that would be simpler in some way or something. And actually, all the solutions I was getting were actually solutions where these were 7 vertices, and they were like orientations of the complete graph on 7 vertices. So I started thinking about why that was happening. And then I actually, from looking at that, I got a general construction for k-out regular C2 free graphs. Take a complete graph on 2k plus 1 vertices. Then every vertex has degree 2k, which implies, this is like a classic graph theory result, that there is an Eulerian circuit W that visits each edge exactly once. And now I just orient each edge according to the direction in which this circuit takes it. So that gives me k-out regularity because I need to enter a vertex and exit it. So one of the edges is of its 2k, k of the edges will be like sort of an entrance, k will be an exit. And this has no C2s because it's an orientation of the complete graph. Now, my last example about gadgets is that a problem I was working on, a particular case of it can be called 4 packing colorings. So the problem here is to color the vertices of a graph with colors 1, 2, 3, 4, so that every pair of vertices receiving color I are at distance at least I plus 1. So here you can see that all the vertices receiving color 1 are at distance at least 2 from each other. The vertices with color 2 are at distance at least 3 of each other, and so on. So here, as opposed to standard graph coloring where a path has chromatic number 2, here the chromatic number is 3. And actually, if you now take this graph, this cannot be packing colored with 4 colors, and there's just no way of filling in this gap, for example. So this is the problem. Can we color the vertices of an input graph respecting this restriction? And the reduction I made was from not all equal 3SAT, which is a variant of 3SAT. The details are not super important. But my original idea was to create a little gadget for each clause where each of these vertices represent the literals. And the way I was thinking about this is that color 4 will represent that this literal is the one that's chosen to be true, which is exactly was going to be exactly 1 in this problem. So I was going to use the colors as a way of saying whether a literal was the satisfied one or not. And a common issue when you do these kind of reductions in NP hardness problems is that you need so-called consistency gadgets to say that if one of your gadgets assign color 4 to a literal that corresponds to, I don't know, the negation of variable x3, and that appears somewhere else, you need to give it the same value, because otherwise you would be contradicting yourself. So it's like, how do you enforce that vertices that are far apart receive the same color? And usually the answer is that you connect them through some subgraph that has the property that whenever you give this color 4, the other one also needs to have color 4. So I encoded this into SAT, and I got the following graph, which has the property that if you color this with 4, this needs to be color 4. And you can also have colored this with 2 or 3, in which case you are not restricted into the coloring of this. So this gadget I also found with SAT. And finally, the last point of my talk is about the hallucination-free property. So how can we trace these SAT solvers? And the answer for the positive case is quite simple. You get a positive solution. You can check even in linear time that it satisfies all your constraints. Usually you can visualize it and just be convinced. The actual question is, what if there's no solution? How you certify that a problem has no solution? That's much harder to do. But fortunately, one of the great things about SAT solvers is that they can emit a proof in a standardized format that certifies this lack of solution. And just to give you a tiny bit of a glimpse without details of how something like that might look like, is that the formula is a series of steps, each of which is telling you some transformation that you apply to the formula. So you have your starting formula, and then you apply some step, so you get an implied formula, and so on a chain until you get a formula that's trivially unsatisfiable, meaning the empty clause. So that must imply that your original thing must have been unsatisfiable to begin with. And obviously, the proof needs not to encode the new formula every time, but just like what the arrow is doing. So it's similar to if you're trying to prove that an equation has no solution, and you start doing a bunch of if and only if steps where you added 1 on both sides, then like exponentiated both sides, and so on until you get 1 equals 0. And then you know that that's false, so therefore your initial equation couldn't have solutions. And a great thing about these proof formats is that there are verified checkers for them. So there's like verified software that receives one of these proofs, and it checks that all the steps actually match and everything is. Yes, these proofs are long. These proofs are long, but they are substantially shorter than the execution trace, than if you were to register actually everything that went into the computation. They're still very long. They can be up to petabytes long.
So this, as you say, they can be verified checkers. So there isn't a way to prove this in a way where the proof time it took you to come up with this trait, this bunch of sort of implications is wrong, but to verify,
yeah, it's much
faster.
Exactly. Yeah, that's like the I guess miracle of the MP class, right? It's like checking is, at least in practice, easier than finding the.
I don't mean just because there's a written proof, but because you can write it in a format, different format,
Yeah, and people have work even like in compressed formats as well. For example, yeah, there's a lot of work in like the representations here to make this efficiently checkable and also like simple, because you want to keep the kind of checking code ideally simple so that it's, for example, easier to verify it in lean or something like that, as opposed to a much more general kind of execution trace, which could be really hard to verify. And because of these, there's a starting ecosystem of math results that have improved using SAT solvers that are then proved in lean. So you prove in lean that this formula construction represents your mathematical object. So for example, in the Sudoku case, you would prove that you have like the Sudoku abstract object with its abstract constraints, and you just prove that the clauses of your formula are representing the constraints of the problem itself. So a nice example of the impact that this can make is that an old problem from Lamy is about the existence of a projective plane of order 10. And this problem was, I guess, proven, quote unquote, in the negative in 1989 without SAT solvers, so just with custom code for this application. But the issue is that a custom like algorithm that has like all sort of optimization tricks, and you might be playing around with bits and so on, it's really hard to verify that it's correct. But in 2020, there was a SAT refutation of this with public certificates that are online. You can just download it, check them efficiently in your computer, and be like, OK, this formula has no solution. And then the only remaining part is that the encoding actually corresponds to the problem and not to something else, which is usually much easier to verify than the correctness of some complicated algorithm. So this, to the best of my knowledge, has not been verified in lean yet, but it's much easier to verify than custom code. So now to actually finish, my conclusion is just that I believe that to the mathematician's toolbox, SAT solvers can be added. Thank you.
There's time for some questions. Can I have one request? And that is, can you repeat the question that has been asked?
Oh, yeah.
Yeah. Okay, so thanks for the talk.
I have three different questions. So the first one is, what is special about SAT as opposed to, for example, circuit SAT? The second one, are there some instances of like statements in Lean where it's easy to convert from Lean to SAT? And the last one is like, you know, if people have tried to improve the bounds for Ramsey numbers using SAT solvers.
Yeah. Okay. So I'll start with your last question, which is the easiest. Have people tried to improve Ramsey numbers with SAT solvers? Yes, and sometimes they have succeeded even. Yeah. So there's like both upper bounds and lower bounds that have been improved, or just certain cases that have been fully proved with SAT. So it seems to be a very effective tool. Now it's still pretty far from being able to resolve, for example, Ramsey 5.5 or 6.6 right now, but we will see. About Lean to SAT, so there's more than one actually integrations between Lean and SAT. There's a Lean SAT library, which is, suppose you're in Lean and you're trying to prove some mathematical theorem that maybe is not even combinatorial, but you have a lot of premises that end up being very propositional in spirit. It's like, my group is, has no idempotent elements, or this and not that, and so on. And let's say they're all incompatible, and you would want to be able to, crush that goal and saying like, yeah, this is incompatible. So there's that kind of direction of integration. And there's also a library that we have used to prove that SAT encodings are correct in Lean. That just gives you a bit of the scaffolding and the interfacing for connecting your Lean propositions with the encoding. So you're trying to match the constraints of your problem to these clauses. And can you remind me what your first question was then?
Yeah, what is special about SAT?
Oh, okay.
As opposed to circuit SAT, for example?
Yeah, it's a good question. And there's like highly optimized solvers for other NP-complete problems. And depending on the context, those might be more beneficial. So a classic example of this is integer linear programming, where there's very good solvers as well. And depending on the flavor of the problem, which one will be better. If your problem is very numerical in nature and has multiplications and additions of numbers, sure, you can encode that in terms of the bits into SAT, but it's usually not going to be as good as just like dealing with them numerically. And vice versa, you can treat a very combinatorial problem by representing things with ones and zeros and like subtractions and multiplications for the ends, but that's not going to be as efficient as dealing with it in the SAT way. So it really depends a bit on the context.
Yes, sir.
So more continuous problems, so when your only goal is to optimize something, you only need to get approximate solutions.
Yeah, so about SAT solving in more continuous problems. So there's a couple of examples, but they all have to do with problems that appear continuous at first glance, and then somebody manages to prove that there's a discretization of the problem. So it's like, well, this object might originally be continuous, and we want to study some property, but actually that is the case if and only if this graph on 7,000 vertices has this property. So those are the examples I know. I would be really curious for examples where, of continuous objects that are represented more directly in a combinatorial way. And I can later I can show you a couple of the examples of this discretization thing. But one of them might be the discrete geometry thing, where your problem in principle is about points in the plane with real number coordinates, where you manage to rule out things combinatorially. And then you also asked about these optimization problems, where it's not about yes, no, but about how many, for example. SAT can deal with them directly if the how many property you're doing, let's say binary search on the answer on encoding, there's at least 10, then there's at least 20, at least 40, and so on. That's one way about it. But there's also directly max SAT solvers whose goal is to minimize the number of, or just to say it in a few words, to minimize the number of unsatisfied clauses. So then you can try to make those map to the things that you're trying to minimize or maximize. So yeah, that's one way of going about it.
I have two questions. One is about inequalities. Can we use such solvers to establish inequalities between combinatorial problem counting something versus counting something else?
Yeah, so that's a great question. So you're asking if we can use that solving in problems where, yeah, what we aim to prove is, for example, an inequality. So usually my first instinct would be to try to, again, come up with a discretization. So sometimes an inequality, for example, has to do with the existence of an injection between one set to another. And that injection is something that has a combinatorial encoding because you can create variables for the mapping between one and the other, and that injection can give you an inequality. That could be one way of going about it. When you're reasoning about integers and inequalities, for example, a classic trick is that A being smaller or equal than B corresponds to the existence of some positive C, such that A plus C equals B, for example. I guess I said positive, I meant non-negative. But yeah, so I would tend to see how to use a trick to try to put it again in the framework, but certainly it's not always direct.
So suppose you wanted to do the following. I wonder if anybody's done it. So you have a piece of code, and you'd like to know that it terminates within a certain number of steps. So that's your statement. And this code and all inputs would terminate in two steps. People have thought of encoding those as algorithms.
So yeah, so this is actually a big question in general. How can we use stat solving in software, in code, to verify properties, do, for example, forms of static checking? My answer, perhaps disappointingly, is that it's kind of a non-constructive thing where I know that the answer is yes. There's a lot of people that have been looking into this, but I myself, very oriented towards this math area, so I'm not particularly aware of the kind of techniques they use. But I do know that especially companies are very interested in this kind of use case of stat solving, like for proving invariance. And as you're saying, sometimes, yeah, like in a fixed number of x.
Just termination, that it doesn't blow up or something.
Yeah, and especially if your types are usually finite in some representation, like integers of a bounded number of bits. So yeah, usually that's very convenient to represent. And I think SMT solving might be even, which is like a generalization of stat solving, let's say, it's even more direct for this kind of software verification direction.
Okay, let's end it here. I think there are still many other questions, but let's take them over the break. So let's